I would suggest that you pause the video and try these 3 warm-up problems. Okay, we should have gotten that our domain, the only restriction was that we couldn't have positive 8. With number 2, our vertical asymptote was setting the denominator equal to 0. And notice that our horizontal asymptote, because we had the same degree, we had to divide the lead coefficients. Notice that in problem number 3, as x is approaching 2 from the left, we've got f of x approaching positive infinity. As x approaches negative infinity, f of x is approaching 0. All right, we are looking at section 3.7 today, which is modeling using variation. So what we're going to do today is solve direct variation problems, solving inverse variation problems, we'll solve combined variation problems, and we'll solve problems involving joint variation. So direct variation, let's talk about this. If a situation is described by an equation in the form y equals k times x, k is a non-zero constant, we would say that y varies directly as x, or y is directly proportional to x. The number k is called the constant of variation or the constant of proportionality. Solving these variation problems. These are our steps. We're going to write an equation that describes the given English statement. So essentially, we're giving you a word problem. You're going to create an equation based off of that word problem. We will substitute the given pair of values into the equation in step 1 to solve for k, which once again is the constant of variation. Once we find that k value, we'll substitute it back into the equation that we did in step number 1. So that means that step number 1 will now have variables in an equation except for k, because we just found what the number was for k. And then from there, we'll use the equation to then answer the actual question from the problem. So here is what we're going to do. It says y varies directly as x. So anytime we are varying directly, we know that we want to use y equals k times x. Okay, so the variable that comes before the phrase varies directly is always going to be by itself. Whatever variable comes after that phrase will always be multiplied by that constant variation. Okay, so now they're giving us 2 numbers. They're giving us what y is, and they're giving us what x is. And that's going to allow for us to solve for k. So we're going to plug 112 in for y. We'll plug 4 in for, or sorry, not 4, 14 in for k, or sorry, for x. And now we need to solve for k. Well, that involves us just dividing both sides by 14. And so we get the variable for k to be 8. So that means we really have an equation y equals 8 times x. And now if we use this equation, it says find y when x is 11. So now we're going to substitute 11 in for x, keeping that variation constant 8. So when we multiply, we get then y to be 88. And that would be my final answer. Okay, let's take a look at another example. It says y varies directly as the square of x. So once again, varies directly means that the variable that came before it is going to be by itself. It's going to equal, now k is getting multiplied by whatever comes after that phrase. Well, it says the square of x. That means we want x squared. So now they're giving us numbers to plug in for every variable except for k, and that's going to allow us to solve for k. So we want 294 to go in for y. We don't know what k is. I know that I want x to be 7. So I'll square 7 and get 49, which is being multiplied by k. I'll divide both sides by 49, and we just found our variable k to be 6. So that means that we really now have y equals 6 times x squared. The last part says find y when x equals 3. So we don't know what y is, but now we want to substitute 3 in for x. So 6 times 3 squared. Well, 3 squared is 9. 6 times 9 is going to give us the value of y to be 54. So that's varies directly. Let's talk about inverse variation. If a situation is described by an equation in the form y equals k divided by x, k is a non-zero constant, we say that y varies inversely as x, or y is inversely proportional to x. K is still called that constant of variation. So when it's direct, we have a multiplication problem. When it's an inverse, we have a division problem. So let's take a look at an example. It says y varies inversely as x. So my setup is that y equals k divided by x. Once again, whatever variable comes before the phrase is by itself. Whatever variable comes after it, in this case, because it's inverse, we're dividing, that goes in the denominator. So now they're giving us what the different values are so we can solve for k. Y is 36. X is 5. To get k by itself, I got to get rid of that division. So I'm going to multiply both sides by 5. So that means that we get a value of k to be 180. So that means that we really have the equation y equals 180 divided by x. So now it says find y when x is 24. So I don't know what y is, but now I know that I can plug 24 in for x. So 180 divided by 24 looks like we're going to get y to be 7.5. Combined variation. In combined variation, direct and inverse variation occur at the same time. So remember, direct is when you're multiplying that constant of variation by x or whatever variable they tell you. And then inverse is when we're taking that constant and we're dividing. So now we're putting them together. So it says the number of minutes needed to solve an exercise set of variation problems varies directly as the number of problems and varies inversely as the number of people working to solve the problems. Okay, so there's a lot to unpack there. I think what I'm going to do first is I'm going to define the situation with different variables. So if it says the number of minutes needed to solve an exercise set, that means that number of minutes I'm going to represent as m. So I'm going to use the variable m anytime I'm talking about the number of minutes. Okay, it's talking about the problems. It says the number of problems. Okay, so if we're talking about the number of problems, I'm going to use the variable n. Okay, so number of problems. If we're talking about then also dealing with the number of people working on the problems, I'm going to use the variable p to represent the number of people. Okay, so those are the three variables. So it's not always like x, y, k. Well, k is always going to be there, but x and y might not be. It might be whatever variable you decide to use. So now I'm going to use those to set up this problem again. Okay, so one more time if I read it. The number of minutes needed to solve an exercise set of problem varies directly. So I know that was a lot of information before that first set of like vocab, but remember, whatever comes before varies directly needs to be by itself. So number of minutes was that phrase. So we want to have m to equal. So that means if it varies directly, it's being multiplied. So notice how it says the number of problems. We want n to represent the number of problems, so that means that our constant variation is going to be multiplied by n. But then it says that we're dealing with the inverse, inversely as the number of people working to solve the problem. Inverse means that we're dividing. P represented the number of problems, or no, sorry, number of people. So this is my basic setup. So now we need to solve for k. So it says that it takes 4 people. So remember, that's going to go in for P. So I know that we're going to have 4 at the bottom. We've got 32 minutes to solve 16 problems. 32 minutes means that that's going to be the M value, but then K is going to be multiplied by the number of problems, so it's going to be multiplied by 16. So here is how we're going to then set up to solve for K. So a couple different ways we could do this. We could get rid of the division first by multiplying both sides by 4. However, if you take a look, these numbers right here are divisible. You can divide. 16 divided by 4 is going to be 4. So we'll have 32 to equal 4 times K. So then I can divide both sides by 4 here, and I get K to be 8. Okay, so now I really have M equals 8N divided by P. All right, so now the last thing says, how many minutes will it take? So we don't know what M is, so we're going to keep M for right now. But we know that it has 8 people to solve 24 problems. Remember, 24 is going to represent N, so that needs to be multiplied by 8. But then it says it takes 8 people, so we're dividing by 8. So hopefully you notice that, hey, 8 times 24, but then divided by 8. The 8's essentially are going to cancel, so it looks like we are dealing with 24 minutes. All right, let's talk about joint variation. Joint variation is a variation in which a variable varies directly as the product of 2 or more other variables. Thus, the equation y equals k times x times z is read y varies jointly as x and z. So let's take a look at this example. It says x varies jointly. So remember, whatever comes before that vocab is going to be by itself. So this time it's x that's going to equal. If it varies jointly, that means that k is going to be multiplied by several things. It's going to be multiplied by z, and it's going to be multiplied by the sum of of y and w. So the sum means that we have 2 things that are going to be added, but once again, everything needs to be multiplied. So that's what my basic setup is going to look like in this particular problem. So we wrote an equation that represents the situation, and now instead of actually solving for any specific variable in terms of numbers, it just wants us to solve the variable. It wants us to get a new equation and solve for y. So this kind of takes us back to some lessons that we've done in previous chapters. Okay, we've got this equation. How do I get this different variable by itself? So there's a couple different ways that we could go about doing this. One way is distributing that kz so we can get rid of the parentheses. So if I distribute, we would have kzy plus kzw. If my goal is to solve for y, I need to get y completely by itself. So I'm going to move any terms away that do not have that variable. So I'll subtract that kzw. So we'll have x minus kzw to equal kzy. So then my last step is, okay, everything next to y is being multiplied. So the opposite of that would be division. So I have to divide everything then on the left also by kz. So then we will get the y by itself. And if you want, you can leave it as this one big fraction, because notice that the numerator doesn't factor any further. Like there's no GCF, so I can't take anything out to see if I can do that. Otherwise, I could break it up individually. So like I said, this could be my answer. Or if I actually wanted to divide it, I could think of it as x being divided by kz minus kzw being divided by kz. So then that would technically simplify then into the first fraction not changing, but then the kz's are going to simplify, so then it would just be minus w. So either way, those 2 things right there are equivalent. But I'm okay if you just leave it as that one big fraction. Okay, let's look at another example. It says the height that a ball bounces varies directly as the height from which it was dropped. So we're talking about a varying directly. So this is actually taking us back to the very first type of problem that we talked about. Okay, so depends on what you want to use for variables. It doesn't really matter, but notice that what comes before varies directly is the height that a ball bounces. So I think we're talking about bouncing, so I'm going to let that be represented as B. So B is going to equal K being multiplied. The second part says the height from which it was dropped. So we're talking about height, so I'm going to represent that as H. All right, so the next sentence says a tennis ball dropped from 12 inches, bounces 8.4 inches. Okay, so it's bouncing 8.4, so that's going to be B. And the height that it was dropped is going to be 12. So then I'm going to divide both sides by 12. So it looks like K is going to be 0.7. So we have now B equals 0.7 H. So from what height was the tennis ball dropped if it bounces 56 inches? So they're telling me what it bounces. We don't know the height that it was dropped. So to solve for our height, we're just going to have to divide by this 0.7. So it looks like my height was dropped at 80 and my units are inches. All right, I would suggest that you pause the video and try these two checkpoint problems. Okay, the first one was varying jointly. So notice that meant that we needed to be multiplying multiple pieces together. So X and Z got multiplied by K. And then at the end, we should have gotten Y to be 240. In the second one, we're talking about varying inversely. Inversely means division. So I know that our temperature then at the end is going to be 0.88 degrees Celsius. So that's us doing all these different types of variation problems.